So in this work, we're looking at two different multi-cell interference mitigation schemes, namely large-scale MIMO and network MIMO. Interference cancellation, the two networks is enabled in different ways. In network MIMO, everything is coordinated, so base stations share CSI and data symbols and they jointly transmit to the users. Large-scale MIMO doesn't have that backhaul communication or coordination, but instead it has a larger number of antennas. So if you look at an example, if you look at just one cluster of such networks, we can see that we have two base stations serving two users and two base stations serving the same two users, right? In network MIMO system, let's say each base station has only a single antenna, right? But the two base stations can share the CSI and data symbols of the users between each other, and once they do that, they can jointly transmit to the users. In large-scale MIMO, though, the backhaul links are not there. There is no communication between base stations. But instead, base stations have a larger number of antennas. For example, in this case, base station 1 has two antennas, so it can serve its own user. And at the same time, if it knows the CSI of the cross-link, it can cancel interference to the other user, right? So these two systems have some common aspects. For example, power per beam or per user is the same in the two systems. And CSI acquisition overhead is also the same because we're considering only TDD networks, and in TDD networks that overhead scales with the number of users, and both systems are serving the same number of users. Further, because of the zero forcing beamforming, the degrees of freedom per user or diversity order per user is also the same. For example, in this case, two antennas are serving two users, so the diversity order of each user is 1. Here, each base station has two antennas serving one single antenna user, but at the same time sacrifices 1 degree of freedom for interference cancellation, so again diversity order is 1. But they have different propagation characteristics. So if we look at the same example, we see that the channel to user 1 has two components, G11, G12 in this case, and the same G11, G12 in large-scale MIMO. So G11 and G11 in these two different cases are statistically the same, but G12 in network MIMO is statistically weaker than G12 in large-scale MIMO. So intuitively, we expect that the channel vector to be stronger on the large-scale MIMO than in network MIMO. So we use that intuition, and using the distribution functions of the channels and the signals, we showed that the signal power on the large-scale MIMO is stochastically, in first order, stochastically dominates the signal power on the network MIMO. But the other thing is the inter-cluster interference. Using the distribution of the channels, again, we could show that for any user location, inter-cluster interference power has the same distribution under the two systems. So we have the stochastic dominance of the signal power, equivalence in distribution of the intercluster power, and then we use some tools from stochastic orders to combine these two and show that in this theorem that for any general class of utility functions, large-scale MIMO outperforms network MIMO. And this is under zero force beamforming and equal power allocation. We have some simulations to show that, for example, the ergodic rate is always better on the large-scale MIMO. But numerically, we also show that if you relax the beamforming scheme and use, for example, instead of zero forcing, we use regularized zero forcing, the same conclusion holds true as well. Thanks.